Hi, welcome back. I wanted to do one more example that is an application for which polar integration is very helpful. So let's look at this example of a probability density function. We were talking before about an archer shooting at a target. Here we have a circular target, polar, and the archer hits the target with a certain probability density function. This probability density function is 2 over e divided by e minus 1 times e to the negative x squared plus y squared. So this question has two parts. First, confirm that this is a probability density function. And then B, determine the probability that the archer hits the bullseye that's in the center of the target. So we have our outer target. It's of radius 1. And then we're going to say there's a bullseye in the middle. What's the probability that the archer is going to hit the bullseye? All right, so what do we need for our function to be a probability density function? We need that it is always positive. F of xy is greater than 0, greater than or equal to 0 for all x and y. And we need that the double integral over the domain of f of xy dA is equal to 1. We need that the sum of all the probabilities for this region is going to be equal to 1. So let's set this up. So question mark, how do you determine whether the double integral of f of xy dA is equal to 1? So in this case, if we look at this equation, we have another clue that this should be a polar integral. X squared plus y squared, that's equal to r squared. So we have an integral where r goes from 0 to 1, and then theta goes from 0 from 0 to 2 pi of our function, which is 2e over e minus 1 times e to the minus r squared times r dr d theta. Okay, so this looks like a function, a substitution integral. First, we'll bring out our constant. So we have e to the minus, let's see, I'm sorry, 2e divided by e minus 1. You know what? I'm realizing that I probably forgot the pi. So we're going to see exactly what this integral turns out to be, and then we'll adjust our constant as necessary. So we've got this 2e over e minus 1 integral from 0 to 1 of r e to the minus r squared times the integral from theta is equal to 0 to 2 pi of 1. So this has the dr in it, this has the d theta. So if we let u be equal to minus r squared, du is equal to minus 2r dr. And so this becomes an integral from 0 to negative 1 of 1 over negative 2 times e to the u du. And so 2e over e minus 1. And so now we have to integrate e to the u. We get, so 2e over e minus 1. The 2 cancels out. And so what do we get? We get e to the minus 1 minus e to the 0. And so what do we get? We get 1 over e minus 1, which is equal to 1 minus e over e, which is equal to negative e over negative, so e minus 1 divided by e, and so this whole thing multiplies out to 1. Sorry about this mess, but in the end, this one integral gives us 1. The thing I forgot to deal with is that this integral gives us 2 pi. So what the question should have said is we have an additional 2 pi in the denominator. So if this is our integral, and we had another 1 over 2 pi in here, a 1 over 2 pi here, then in the end, this whole integral would indeed be equal to 1. All right. Nevertheless, we can continue and we can ask, what's the probability? So we've found that this is indeed a probability density function. This integral is at least 1. And then e to every power is always positive. So the function is always greater than or equal to 0 for all x and y. All right, so this is a probability density function. And now we need to show that the probability, we want to figure out what the probability is that the archer hits the bullseye. And so what's that? Well, that is what happens when instead of integrating from 0 to 1, we integrate from 0 to 0.25. So let's set that up. We want to integrate from r equals 0 to r equals 0.25. Integral from theta equals 0 to 2 pi of 1 over 2 pi 2e over e minus 1, e to the minus r squared, r dr d theta. All right, and so as we go through all the bits, the only thing that's changing is that we have this 2e over e minus 1 times the integral from 0 to 1, so 0 to 0.25, of r e to the minus r squared dr, and then this 1 over 2 pi does cancel out with this integral from 0 to 2 pi of d theta. And so what do we get? We get, we have the same substitution, integral from 0 up to negative 1/16 of 2e over e minus 1 times negative 1 over 2 e to the u du. And so what do we get? We bring out the negative 1/2, and we get e over 1 minus e times e to the minus 1/16 minus 1. All right, and so this is our answer. I think I want to use Mathematica to get a much closer answer, and we'll see this a little bit better, what exactly is happening. All right, so let's go over to Mathematica. So we've got this function. Now I'll actually divide by 2 pi, and we'll look at that. And from 0.5. So here is our probability density function. We can see that as a target, the archer is much likelier to hit in the center than on the outside. And so what we can do is we can integrate 2e, and we have to divide by 2 pi. And we have r goes from 0 to 1, theta goes from 0 to 2 pi. And when we integrate that, we get 1. But if we take this integral and instead integrate from 0 to 0.25 in terms of a radius, we get the probability of hitting somewhere in that region is about 9.6%. So the probability of landing there is going to give you that. Let's see what happens if I put 1/4 here. It'll give us the exact value in terms of E. So this is an example of using polar coordinates to integrate. Let's see what would happen if we used non-polar coordinates, Cartesian coordinates. Let's see if Mathematica is able to give us that answer. X squared plus y squared. X goes from -1 to 1. Y goes from negative square root of 1 minus x squared up to positive square root of 1 minus x squared. And if we integrate that, it's thinking really, really hard. I'm going to stop it and ask it just for numerical integration. And so, well, this was the full integral. It does give us 1. And if we did instead, we wanted to integrate from x is equal to negative 0.25 to positive 0.25, and then this is 0.25 squared. This is 0.25 squared. Then we get that same answer of 9.6%. So you can use Mathematica to solve these integrals as well. All right, let's stop there. Take care.